All right, guys, so as we finish up 3.8 in derivatives of inverse trig functions, we're going to look here at the derivative of arc cosine, cotangent, and cosecant specifically. And so what you see on the screen right now is helpful identities, all right? So let me preface this lesson by saying, if you recall from when our previous videos, we almost showed a proof, right? We showed a proof as to how do we derive the formulas for finding the derivative of arctangent, arcsecant, and arcsine. And we could do the exact same thing with implicit differentiation for cosine, cotangent, and cosecant, okay? However, I believe, and most calculus books and mathematicians believe as well too, that there's an easier method to go about this. Thinking about it, it'd be a challenge to remember, 6 different formulas for each of the inverse trig functions. So instead, what we can utilize is we can utilize 3 trig identities in regards to inverse. And that is what you see currently on the screen right now. That the cosine inverse of x is just pi halves minus the sine inverse of x. Cotangent's inverse is pi halves minus tangent inverse. And then cosecant inverse is just pi halves minus secant inverse itself. And that just basically goes back to our knowledge of, how does a reflection over y equals x really look, and what is the comparison between the two inverse functions on a graph. Now, when it comes down to these particular identities, what I want to make clear is that these identities are not the formulas for the derivatives. All right, let me say that again. These are not the formulas for the derivatives. These are identities of cosine inverse, cotangent inverse, and cosecant inverse, in which we already know the formulas for sine, tangent, and secant inverse derivatives. That way, we don't have to memorize brand new derivative formulas. We already know sine, tangent, and secant inverse derivative formulas. And so we can utilize these particular identities to help us make that next step forward and find derivatives of cosecant, cotangent, and cosecant, okay? So if a problem were to ask you, find the derivative of cosecant inverse of whatever function of x, all right? You don't need to find a new formula for cosecant, or for cosine, excuse me. You can instead use your sine formula inverse for the derivative, okay? And do what you need to do to take that inverse and, kind of go along with it. So just please keep that in mind as we're kind of dealing with some of these things. And for our purposes today, our goals of 3.8 are remaining the same. Our goals are to find the inverse trig function derivatives. But today we're going to kind of step aside from just the monotony, I guess, of just, hey, here's a function, find the derivative. We're going to use it a little bit more into application today of kind of recalling what it actually means to find the derivative of a function at a specific value of x, which is the slope of the tangent line itself. So the example that we're going to look at here today, guys, is let's find an equation for the line that is tangent to the graph of y equals cotangent inverse x at the specific point in which x equals -1. So first and foremost, let's think about this for a sec. If x equals -1, that means there is a specific y value for the function at x equals -1. Let's get that out of the way, and let's find what y equals when x equals -1. So this means that y is going to be whatever cotangent inverse of -1 is in fact going to be. All right? Well, let's think here for a sec as to what we're dealing with. For some of you guys, finding cotangent inverse at -1 might be very simple because you are all stars when it comes to the unit circle. I'll be the first one to admit I don't feel that way about the unit circle. And so instead, I'm going to utilize an identity that we just learned because I'm a little bit more comfortable just thinking about tangent more than cotangent itself. So we just learned this is the same thing as pi halves minus tangent inverse of -1. And then we can kind of use tangent to our advantage here as well. And so we got to think for a second, though, is remember what our boundaries are for cotangent, tangent inverse, and all of the same, that we deal with when it comes to finding these particular trig identities. If you kind of think about it, the tangents, personally, right, tangents inverse has a specific domain that we have to stay within for this sign. And the thing about tangent that's kind of good to use is that tangent is differentiable for all real numbers. And so we can use that to our advantage as we're finding our particular inverses. And so if I'm finding the inverse of tangent at -1, we have pi halves, and I know the inverse tangent at -1, that's found at -pi/4. All right? And so we have pi over halves minus -pi/4. This becomes an addition problem, and when we add this together, this becomes 3pi/4. And so now we have just found our point. So we know that we are going to have a point at -1 and 3pi/4. Save that in your back pocket. We'll use it a little bit later. Remember the problem said we need to find an equation for the particular tangent line. Well, remember, the tangent line is found by having the point we just found and the slope. The slope of the tangent line is found by the derivative. So we need to find the derivative of cotangent inverse. So next, we need to find d dx of cotangent inverse of x. So in doing so, I want to utilize the fact that this is pi halves minus tangent inverse of x. Why? Because I already know the formula for tangent inverse of x. I don't want to learn a new one for cotangent inverse of x. So I have tangent inverse of x, and we know that's 1 over 1 plus x squared. We just learned that in the last couple of videos. And so now it's just taking the whole derivative. So the derivative of this entire function. So I need to take the derivative of this entire function. So really, I'm taking d dx of pi halves minus tangent inverse of x. Well, the derivative of pi halves is 0 because it's a constant. Don't think it's pi, because remember, pi is not a variable. Pi is a number. So the derivative of pi halves is 0, and then you have negative tangent inverse of x. And so really, it's just negative of our tangent formula that we've been dealing with for inverse tangent. But we wanted to know this specifically when x was -1, so we can find the slope of the tangent line. And so if you substitute -1 into there, you get -1 over 1 plus -1 squared, which is -1 over 2. So the slope of the tangent line, so this is m, slope of the tangent line for this particular function at x equals -1 is going to be -1/2. And then we just wrap some things on up by using our point slope formula. Y minus our y value, which is 3pi/4, our slope, and x minus that -1. Just simplifying things out a little bit, we get y minus 3pi/4, -1/2 x. This becomes a positive, so this becomes a negative when you multiply it across. And then adding on over, we'll finish up with y equals -1/2 x. This is -1/2 plus a 3pi/4. We'll multiply by 2, multiply by 2. This is really 2 over 4, so it's 2 plus, negative 2 plus 3 pi over 4. So the easiest way to probably keep this is negative 2 plus 3 pi.